Hey everyone, so today's video focuses on program flow and data move instructions when programming with Proficy Machine Edition for an Emerson RX-Ray PACSystem controller, notably the IC695 CPE305. Now when it comes to program flow, there's a couple instructions we'll be touching on, such as run commenting or program block calls and jump and label pairs. And then when it comes to data move instructions, there's all sorts of data types that you can deal with, but we're going to just handpick a few, such as maybe booleans or integers or real values, but I'll be showing you how to move data in between different variables of certain data types. So without further ado, let's get started. We can see here I have Proficy Machine Edition version 9.5 running here, and I have a very simple program. We can see here just under my hardware configuration, I have a very simple configuration set here, so a 7-slot rack with a power supply, my CP305 CPU, and a network module in the rack. And then in terms of my program blocks, I just have the default main routine, and there's nothing in it, so just a blank canvas for us to start programming on. So let's start off with a program flow run comment. Run comments are immensely useful and should be sensible, but also brief and to the point, just so there's no confusion for the programmer who also was writing the code. Now if I click on the comment instruction and I just have a run highlighted, I can just go ahead and place a comment and just go ahead and start saying, hey, this is my first comment. And once we've applied the comment, we can accept our edits and the comment is applied. Now, what's really important is when it comes to comments, they're actually saved in the controller. So if you were to do an upload from an RX-Ray controller and you didn't have the project file, you just want to grab whatever's in the controller and use that to populate your project, it would grab all the comments, obviously in addition to all the code and the hardware configuration. So just really good practice. Make sure you always use comments when you're talking about certain logic. So if you have a very complex set of rungs, maybe add a few comments to explain how the rungs operate, and that way there's no confusion for anyone else who might be viewing your code down the line. Now as a really helpful hint, comments in this case, they don't really stick out to me. I mean, yes, I can see them, but they're not really sticking out to me. Imagine a ton of logic here. So you can just make this a little bit easier for yourself if you really want the comments to stick out. If I go to Options under my project and I just go to Ladder, and I go to Fonts and Colors, if you scroll down, you have all these default colors that have been set to certain types of rungs and parameters and labels, etc. But eventually you're going to find one called comment background. If you set this to yellow, it honestly helps so much. I always like to use yellow as my background for comments, and they just stick out like a very sore thumb. So it's very easy for me to see them and basically discern them away from any kind of logic that may be in between those comments. Now, comments are really helpful because you can also make multiple rows for your comments, like multi-lines. So I can say, hey, line 2, or hey, line 3. I even have spaces in between, or add colons, asterisks, and have hey, line XXX, whatever it might be. So it's really helpful, and just gives you a full flexibility of how you want them to look. So we're just going to accept this edit and write to the PLC. So there you go. So comments in a nutshell. And you can, of course, copy and paste this to have multiple comments in rungs, superseding the comments or preceding the comments, up to you. Now let's talk a bit about program block calls. Calls are really helpful, and they're useful because it allows you to basically call different program blocks to help segment your code. Maybe you have a program block which handles, say, some arithmetic calculations, whereas maybe another program block will handle, say, some other if conditional statement calculations. So why don't we do a quick example? What I'm going to do is just go offline. I'm going to create these edits offline. It's going to be a lot quicker for us, and it will allow us to just do everything at once instead of being able to do multiple online edits. So the first thing I'm going to do is under my program blocks, I'm going to call a new ladder diagram block. I'm going to call this block my underscore block underscore 2. And in this block, I'm going to jump to it. We'll see a tab open for it in our PME here. And I'm going to have a very simple logic set here. I'm going to call this add int. And what I want to do is every time this instruction is called, so called as add int please, I want to add 1 to an integer called my int, and I'm going to go ahead and add it back into itself, so it's obviously just accumulating. And then we're going to jump back to our main routine, and I'm going to create another normally open conject called calculate int, and use a positive con or a positive transition coil, and that's going to write to our variable called add int please. And I'm using a positive transition contact because I only want this to be true for one scan on the rising edge when we execute our calculate integer in a variable instruction. Now, once this hits on the rising edge, we're going to want to have to call our my block 2 from the main routine, which is basically the flow of the program. So to do that, it's very, very simple. You can do it in two means. You can either just go to instruction and type in call, and then once you have the instruction here, I'm going to just copy this over here, just have some horizontal wires, and then just click the call instruction and literally just type out my block 2. It's going to automatically scan and figure out what blocks are available to you, and it will say my block 2. The other way was to just simply click this little call icon, and it will do the same thing. You click it, you paste it, and then you have a call instruction. So as you can imagine, call instructions are immensely useful and just help segment your program. So let's just reevaluate this. So when I do the download, we're going to just go to target, go to connect, and we're going to do a download to a program. So I'm just connecting to it. Let's click on programmer mode because we got to be in programmer mode to do our download. And then we're going to click the download button, click on download, and then just basically allow this to download to our PLC. Okay, so basically what's going to happen is the main routine is the first program block that gets executed during the scan cycle. So as it scans from top to bottom, beginning with rung 1, well, it's just a simple comment. So rung 2, it will check to see if calculate int, if the variable is true. If it's true, it's going to set add int please to 1 just for as a pulse. So this is just a positive transition coil, and then it's going to cause my block 2 to be called, whereupon further down the line, this rung 1 of our block will be executed, and because add int please will be equal to true, it's going to go ahead and call and execute our add integer instruction to add 1 into my int onto itself. So if we go back to main and I go ahead and toggle this variable, there we go, calculate int is on. We should have caught that positive transition when we call my block 2. Because we're still in the scan cycle, we haven't finished that transition. My block 2 will be called, and we can see here we executed our add integer instruction. Now if I go ahead and I just set this back to 0 and I do it again, we can see here that we're now at a value of 2. So we know the logic is working. So as you can imagine, call blocks are very useful and again help you to break up your code so you're not writing everything on a single ladder diagram block. As an example, you can break it up into different blocks, so you can have multiple call routines one after another. Cool. And finally, what I want to show you in terms of program flow is our jump and label pairs. They are useful. You may not be using them very frequently, but they do have their place. So let's go ahead and add in a normally open contact and call this execute label. Execute label. And we're going to have a, we'll just put a coil here, and we're going to do a jump instruction. Jump n is the instruction. Then we're going to just leave some room for some code, and then we're going to add a label. So I'm going to just place our instruction and call this our label n. And basically how a jump label pair works is whenever you energize a jump n instructions, it essentially jumps to the code, the rung, where the matching label is shown. So if I call this my label, and I just double click this jump n and just use my label, then when this executes, meaning power is passed from left to right, the PLC will basically jump over any rungs in between the jump and label instruction and continue executing from the label. So you would basically bypass any code between the jump and label instruction. So imagine this, if I had a simple code here called contact1, and then I have a coil called coil1, and I save this. What's going to happen is, as long as we're not passing power to my label, or excuse me, to the jump n instruction, it's not going to jump over this second rung. So right now, power is not being passed, so if I energize contact 1, the output coil 1 energizes. If I leave it off, coil 1 is off. But if I were to execute our label variable, it's going to pass power to the jump n instruction, which then jumps to the my label label n instruction. And then basically what will happen is, if I try to energize contact 1, we can see here, even though we're energizing this contact, the output is not being energized because this code is not being evaluated. This rung is not being evaluated. The variables are left untouched. Now the inverse is true. If I just de-energize execute label and I were to energize contact 1, and then I executed my label, so now we're at jump n, go over the code and jump to my label. If I try to de-energize contact 1, we can see your coil 1 is left in the last known state before I energize the aforementioned rung. So again, jump and label pairs are very useful, so any logic in between the jump and label ends remains unaffected. We just leave it in the last known state. You can, of course, override the variables themselves. I can start playing with this coil 1 and I can energize or de-energize it as I so desire to change the state of the variable in the program. But the code execution of rung 2 will not take place because we are effectively jumping over this logic. Now, if I disable execute label, we're going to see this coil turn back to off because now it's executing logic and it sees contact 1 is de-energized. Therefore, the coil is de-energized. So, very useful. What I've seen this being used is during startup routines. Typically, on the first scan, when a PLC is starting up and it's just started executing, you may want to prohibit any sort of logic execution in your PLC for a few seconds, maybe to let your input stabilize. And then only after, say, a timer delay, you can begin execution of downstream logic. That's one typical example. Another could be for a failure scenario. Maybe you want to prohibit execution of certain logic if there is a failure for an input or maybe an internal fault in the controller. So just to help capture those faults and manage those faults. There's another example that you could do. Okay, let's jump to move instructions. These are immensely useful, but very, very, very simple to use. So what I'm going to do is I'm going to just ensure my label is on because we're not going to disturb this execution, and we're going to allow, we're actually going to allow us to, no, you know what I'm going to do? I'm going to just remove this logic. Let's just simply remove it. Let's start off with a blank canvas. Now, as mentioned before, the data move instructions are available to us for a variety of data types because they're so useful. They're very, very applicable for all sorts of logic. So I could do a move bool, or a move real, or a move int, or a move long real, etc., etc. There's all sorts of move instructions. So let's suppose I have this move real instruction. Let's move a real value. So let's call this my real 1, and let's call this my real 2, and let's add a coil here and call this, a contact here and call this move values, and we'll add our horizontal line to manage the gap to ensure power is passed to the instruction. Now, what's going to happen here is, as soon as power is passed, whatever value is in my real 1 will then move to the variable my real 2. So if I make this say 4, and then I energize move values, a 4 will be written to my real 2. And if I continue passing power, and I might have 3 here, then power will be passed, and so forth and so forth. Now, if I disable move values, and I were to write a 3 here, then it's not going to move to my real value 2. If I write a 6 here, that's fine, and then if I energize again, then we'll move it back to 3. So as you can imagine, these are very useful for moving data between different variables and handling data between different data types. And that's basically it for data move instructions. I'll do another quick example. I could even have another one here in the same rung, just on the right-hand side, and I'm going to call this move int. So this move integer instruction and move real instruction will execute whenever we have move values enabled. I'll call this my integer 1, and I'll call this my integer 2. And let's go ahead and just accept these edits, and when we've accepted them, we're going to play with our integer values. So right now, my int 1 is equal to 6, whereas my integer 2 is equal to 5, and if we energize move values, well, we're moving the value from my integer 1 to my integer 2. And as long as we have it energized, we can see it's constantly moving those values over. So I hope this video was very informative, and thanks for watching.